The cosmos holds secrets we have not yet learned to see. For all our telescopes and probes, the universe is dominated by a substance that remains invisible, a ghostly presence we call dark matter. But what if this dark matter could clump together, not just in vast halos, but into singular, stellar-scale objects of immense power? These are dark stars, theoretical giants from the dawn of time that could rewrite our cosmic history. By the end of this exploration, you will understand 25 specific, undiscovered dark stars that could be hiding in plain sight, from the empty voids between galaxies to the chaotic heart of our own Milky Way. We will venture into how they might form, where they could be lurking, and the strange signatures that could betray their existence. What if the oldest objects in existence are not stars at all, but something far stranger, and they are waiting for us to find them? What does it mean to look for something defined by its absence? Our journey begins in the most desolate neighborhood in the known universe. The Boötes Void is a staggering sphere of near-nothingness, a cosmic desert so vast it could contain thousands of galaxies, yet holds only a handful. Within this profound emptiness, astronomers propose our first candidate could be hiding, a dark star of truly primordial origin. We are calling it the Primordial Behemoth. To understand why this location is so compelling, we must travel back to the universe's infancy. In those first chaotic moments after the Big Bang, the cosmos was a seething, opaque soup of particles. Ordinary matter, the stuff that makes up stars and planets and us, was thoroughly mixed with dark matter. As the universe expanded and cooled, gravity began to pull at these particles. In most regions, ordinary matter clumped together first, eventually igniting into the first generation of brilliant, fusion-powered stars. But what if, in a rare pocket of space, the dark matter was unusually dense? Here, a different process could have unfolded. A vast cloud of hydrogen and helium, laced with an extraordinary concentration of dark matter, could have begun to collapse under its own weight. As it shrank, the ordinary gas would have heated up just as it does in a normal star-forming cloud. But in this scenario, the primary source of energy would not be nuclear fusion. Instead, the dark matter particles at the core would annihilate upon contact with each other, a process releasing a tremendous flood of heat and radiation. This heat would counteract the gravitational collapse, creating a stable, gigantic object. The primordial behemoth would be a star in appearance only, a colossal sphere of glowing hydrogen powered not by a central furnace, but by the ghostly self-destruction of dark matter at its heart. It could have been one of the very first large structures to form, a lighthouse in the dark ages of the universe. Its incredible mass, perhaps hundreds of times that of our Sun but concentrated in a different way, would have exerted a gravitational influence far beyond its visible light. This leads to a fascinating possibility. Could such an object have actually helped create the Boötes Void itself? If this dark star formed exceptionally early, its powerful gravity could have repelled the normal matter needed to build galaxies in its vicinity. Over billions of years, as the universe expanded, this region would have been left behind, a growing bubble of emptiness centered on the ancient, unseen giant. Finding it would be a monumental challenge. It would not shine with the familiar signature of fusion. Instead, we would be searching for a subtle, diffuse glow of certain wavelengths, perhaps in the infrared, or for unexplained gravitational lensing effects in the void's deepest recesses. The primordial behemoth represents a perfect starting point for our list, a relic from a time before stars as we know them even existed, potentially sitting at the center of the greatest nothing we can see, holding the secret to how cosmic structures first began. Detecting a dark star is not a matter of seeing light, but of observing the absence where its gravity bends reality. The primordial behemoth's most likely calling card would be a gravitational anomaly, a subtle warping of space-time in the heart of an already empty place. To find it, astronomers would turn to a phenomenon called gravitational lensing. This occurs when a massive object, like a galaxy cluster, acts as a cosmic magnifying glass. Its immense gravity curves the fabric of space around it, bending the light from even more distant objects that pass behind it. This distorts and sometimes multiplies the images of those background galaxies, creating arcs and rings of light. But the primordial behemoth presents a unique and far more difficult case. It is not a vast cluster of galaxies, but a single, incredibly massive object. And it sits in a void where there are very few bright background galaxies to distort in the first place. This is the core of the challenge and also the key to its potential discovery. Instead of looking for dramatic arcs, scientists would search for a much subtler signal, a statistical anomaly. They would meticulously map the precise shapes and orientations of every faint, distant galaxy whose light passes through the Boötes void. A normal patch of empty space would leave these shapes random, but if a supermassive dark star lurks within the void, its gravity would impose a tiny, coherent distortion on all the galaxies behind it. It would be as if you looked through a perfectly polished, invisible lens at the distant universe and saw every single star in that view very slightly stretched in the same direction, pointing toward the hidden mass. Finding this signal is like listening for a single, pure note in a room filled with chaotic noise. The void's emptiness actually helps because there are fewer competing sources of gravity to confuse the measurement. Yet the signal itself would be incredibly faint, requiring the most sensitive telescopes and years of patient observation. Confirming such a detection would be a monumental achievement, providing not just evidence for a dark star, but direct proof that dark matter can coalesce into singular stellar-scale objects. It would mean the oldest giant in the cosmos has been hiding in the quietest place imaginable, its presence written only in the bent paths of ancient light. While the primordial behemoth hides in a cosmic desert, our next candidate thrives in the most crowded and violent neighborhood imaginable. Deep within the chaotic core of our own Milky Way, a dark star may be locked in a deadly dance with the monster at our galaxy's center. This is the galactic core parasite, a theoretical object orbiting perilously close to Sagittarius, a star, the supermassive black hole that anchors our entire spiral system. The environment here is unlike any other, a place of crushing gravity and frenetic motion where stars whip around the black hole at breathtaking speeds. Among these stars is one named S2, a well-studied object that completes a single, frantic orbit in just 16 years. Astronomers have mapped its path with exquisite precision, and it is here, in the subtle wobbles of this star's trajectory, that the parasite might reveal itself. The concept is this: as stars and gas clouds spiral toward the central black hole, they are not alone. Theoretical models suggest that dark matter, drawn by the immense gravity, also piles up in an extraordinarily dense cloud around Sagittarius, a star. Within this dense halo of invisible matter, a dark star could form or be captured. This object would be a parasite in the truest sense, not feeding on light or gas, but on the abundant dark matter reservoir itself. Its annihilation engine would glow faintly, a dull ember against the brilliant backdrop of crowded stars and swirling hot gas. But its most significant feature would be its mass, a tremendous gravitational signature hidden in plain sight. If such a massive, unseen object were orbiting near the black hole, its gravity would tug on everything around it, including the star S2. The predictable, clockwork ellipse of S2's orbit would show tiny, unexplained deviations, a slight wobble or a periodic shift that cannot be accounted for by the black hole's gravity alone. It would be as if you were watching a meticulously choreographed ballet, and one dancer consistently stumbles at the same point in the music, suggesting an unseen partner pulling them slightly off course. Discovering these perturbations would be a detective story written in the language of gravity. Astronomers would not need to see the parasite's faint glow, which would likely be drowned out by the galactic center's intense radiation. Instead, they would scrutinize decades of data on S2 and its stellar neighbors, searching for a consistent pattern of disturbance that points to a second, invisible source of mass. Finding the galactic core parasite would be a revelation on two fronts. First, it would confirm that dark stars can exist in the modern universe, not just in its primordial past. Second, it would provide a stunning new tool for mapping the invisible dark matter distribution at the very heart of our galaxy, using the orbits of stars as our probes to trace the outline of something we cannot see. The chaotic core of a galaxy is one place a dark star could hide, but there is another, even more isolated realm it could call home, far beyond the last outlying stars of the Milky Way. In the profound and empty gulf that separates us from the Andromeda Galaxy, a lone wanderer may be drifting through the eternal night. This is our third candidate, the Rogue Wanderer, a dark star cast adrift in intergalactic space with no stellar companions and no galaxy to call its own. Its origin story is one of cosmic violence and loss. Billions of years ago, when the universe was younger and more crowded, small primordial dwarf galaxies swarmed around the emerging giants like our Milky Way. During a long-forgotten merger or a close gravitational encounter, a dark star at the heart of one of these tiny galaxies could have been violently ejected. The gravitational slingshot from the merging black holes or the chaotic dance of stars could have flung it out into the void at tremendous speed, sending it on a journey with no destination. It would have been stripped of any remaining gas or visible stellar companions, becoming a perfect, isolated sphere of dark matter annihilation, glowing faintly as it travels through absolute nothingness. This very isolation is what makes the Rogue Wanderer perhaps the most elusive dark star of all. The primary method for finding massive invisible objects, gravitational lensing, relies on a backdrop of distant light to be distorted. In the deep fields between galaxies, that backdrop is almost non-existent. There are no rich clusters of background galaxies to create lensing arcs, and no foreground stars to show a wobble in their motion. The Wanderer is a ghost moving through a ghost town, leaving almost no trace in its wake. Yet, there is one fleeting chance to catch it. Astronomers would rely on a more subtle phenomenon called microlensing. Imagine this dark star on its endless journey happens to drift directly between our telescopes and an incredibly distant, brilliant beacon known as a quasar. The quasar's light, traveling for billions of years to reach us, would pass very close to the dark star's immense gravitational field. For a brief period, perhaps days or weeks, that gravity would act as a tiny lens, focusing and brightening the quasar's light in a specific, predictable way. It would be a single, unexplained spike in the quasar's brightness, a flash in the data with no other cause. Detecting such an event is a monumental task of patience and precision. It requires continuously monitoring thousands of quasars across the sky for years, waiting for that one chance alignment. The signal would be transient and unique, a signature that cannot be repeated or double-checked. Finding the Rogue Wanderer would be a testament to both cosmic serendipity and relentless scientific observation. It would prove that these objects are not confined to galaxies, but can exist as solitary nomads in the vastest expanses of the cosmos, their faint glow a lonely beacon in the endless dark. A lonely neutron star spinning hundreds of times per second can be the most precise clock in the universe. Its rhythmic pulse, beamed across space as radio waves, arrives at our telescopes with metronomic regularity. But what if that perfect cosmic clock begins to tick a fraction of a second early or late for no apparent reason? This anomaly is the clue that leads us to our fourth dark star candidate, the dark binary companion, an unseen partner locked in a gravitational embrace with a visible stellar corpse. The scenario unfolds with a pair of stars born together. One, a massive star, lives fast and dies young, exploding in a supernova and leaving behind an ultra-dense, city-sized remnant called a neutron star, often observed as a pulsar. Its companion star, however, follows a different path. Instead of becoming another neutron star or a black hole, it is a vast cloud rich in dark matter. As the visible star explodes, the shockwave could trigger the collapse of this dark matter cloud, igniting the annihilation engine at its core and birthing a dark star. The two objects, one a brilliant ticking pulsar and the other a faint, massive sphere of dark matter, would then orbit a common center of gravity. The pulsar's incredible regularity is the key to the discovery. Astronomers use instruments called pulsar timing arrays, which are essentially networks of radio telescopes listening to dozens of these cosmic lighthouses. They measure the arrival time of each pulse with astonishing precision, down to a few hundred nanoseconds. In a stable, isolated system, the pulses are perfectly predictable. But if the pulsar is being tugged around by a massive, unseen companion, its rhythm will be disrupted. As it moves toward us in its orbit, the pulses arrive slightly more frequently. As it moves away, they arrive slightly less frequently. This creates a distinct, repeating pattern in the timing data, a wobble encoded in the ticks of the clock. By analyzing this pattern, scientists can calculate the mass and orbit of the invisible object doing the pulling. If the calculated mass is substantial, perhaps many times that of our Sun, and no light at all can be detected from that location, the evidence points to something extraordinary. It would not be an ordinary star, a planet, or even a typical black hole, which often reveal themselves by sucking in gas from a companion. This would be a massive, dark, and stable object whose primary signature is pure gravity. Finding a dark binary companion would be a direct and elegant detection, using the universe's own most precise instruments to reveal a hidden partner. It turns a catastrophic stellar death into the birth of a unique cosmic partnership, one where a spinning beacon of light is forever bound to a silent sphere of shadow, its secret told in the subtle drift of a radio pulse. The universe's oldest stellar cities hold secrets within their crowded streets. Orbiting the Milky Way are ancient globular clusters, dense spheres of hundreds of thousands of stars, all bound together by gravity and born from the same primordial cloud. Among the most famous is Omega Centauri, a glittering metropolis of suns that has existed for nearly the entire history of the cosmos. In such an ancient and crowded environment, where stellar interactions are constant and gravitational tides run deep, a different kind of resident could have formed and survived. This is our fifth dark star, the fossil in a globular cluster. To understand why this location is so promising, we must think of these clusters as cosmic time capsules. They formed when the universe was young and rich with both ordinary and dark matter. As a globular cluster condensed from a vast cloud, it is possible that a particularly dense knot of dark matter was trapped at its very heart. This dark matter core, surrounded by a shroud of hydrogen and helium, could have ignited its annihilation engine long before the first fusion-powered stars in the cluster fully matured. The result would be a dark star, a massive and stable object sitting at the cluster's center, influencing everything around it for billions of years. Its presence would be felt, not seen. Astronomers studying the motions of stars in some globular clusters have noticed something peculiar. The velocities of stars near the core do not always follow the expected patterns based on the visible mass alone. Some stars move faster than they should, as if being whipped around by an additional, unseen source of gravity. This is where the fossil could provide the answer. A massive dark star at the cluster's core would act as a gravitational anchor, subtly sculpting the orbits of the visible stars. It would be like watching a busy roundabout where all the cars are moving just a little too fast, hinting at a massive, invisible structure buried beneath the asphalt that affects the flow of traffic. Detecting this fossil would require meticulous stellar cartography. By mapping the precise speeds and trajectories of thousands of individual stars in a cluster like Omega Centauri, astronomers could build a detailed model of the gravitational field at its heart. If a significant point of mass reveals itself through these stellar motions, and no corresponding bright object or black hole accretion disk can be found, the case for a dark star grows strong. Finding the fossil would be a direct link to the earliest chapters of star formation, proving that dark matter played a hands-on role in building the oldest structures in our galactic backyard. It suggests that within these beautiful, ancient spheres of light, a shadow from the dawn of time may still hold sway, its silent gravity writing its signature in the dance of ancient suns. Gravitational lenses can create some of the most beautiful and bizarre sights in the cosmos, but one particular formation stands out as a perfect cosmic puzzle. The Einstein cross is a stunning arrangement where a single, distant quasar appears to us as four distinct images, arranged in a cross-like pattern around a foreground galaxy. This happens because the immense gravity of that galaxy bends the quasar's light, splitting it into multiple paths that converge at our telescopes. It is a textbook demonstration of Einstein's theory of general relativity, but what if the textbook is missing a crucial page? Our sixth dark star candidate, the lens in the Einstein cross, emerges from a subtle inconsistency within this very phenomenon. Astronomers can create incredibly precise models of these gravitational lenses. By studying the exact positions and brightness of the four quasar images, they can calculate the total mass of the foreground object causing the distortion and how that mass is distributed. In a standard Einstein cross, the lens is a visible galaxy, and the model's predicted mass aligns well with the observed starlight. But imagine a case where the math does not add up. The models might reveal that to create the observed bending of light, the lensing object must possess a mass far greater than the sum of all the stars and gas we can see in that foreground galaxy. Even more intriguing, the models might suggest that this extra mass is not spread out in a diffuse halo, but is instead concentrated in an unusually dense, point-like region near the galaxy's core. This is the signature of a potential dark star. It would be as if you were trying to balance a scale. On one side, you place all the visible matter of the galaxy. On the other, you place the required mass determined by the bent light. The scale tips dramatically, indicating a heavy, unseen weight on the visible side. That hidden weight could be a singular, monstrous object composed primarily of dark matter, its annihilation heart glowing faintly but its gravity dominating the local spacetime. Its presence would warp the paths of the quasar's light in a unique way, adding a subtle, extra distortion that pure starlight cannot explain. Proving this would require painstaking work. Astronomers would take the most detailed observations of an Einstein cross, measuring not just the image positions, but also their precise time delays as light takes slightly different journeys along each path. They would run countless computer simulations, testing every possible configuration of normal matter. If all conventional models fail to reproduce the exact pattern seen in the sky, and the only solution is to insert a massive, compact, and dark object at a specific point, the case for a dark star lens grows compelling. Discovering the lens would transform a beautiful cosmic coincidence into a profound clue. It would mean that within a known galactic lens, a shadowy titan hides, its immense gravity not just bending light, but bending our understanding of what can anchor an entire galaxy's core. The serene precision of a cosmic clock gives way to a scene of celestial chaos. Some galaxies do not simply form stars, they erupt in a violent, brilliant fever. Messier 82 is such a place, a starburst galaxy where stars are born in frantic, superheated clusters, blasting out fierce winds of gas and radiation. At the heart of this maelstrom, our seventh dark star could be hiding, not as a silent fossil, but as an active engine of destruction and creation. We are calling it the dark matter fountain. The theory begins with the unique environment of a starburst core. Here, unimaginable densities of gas, dust, and stars are in constant, turbulent motion. This ordinary matter is swimming in what should be an equally dense sea of dark matter. the invisible scaffold that holds the galaxy together. In this extreme crucible, something extraordinary might occur. A vast cloud of dark matter, funneled to the galactic center by the tumultuous gravity, could collapse under its own weight. But instead of forming a quiet, stable dark star, the process might become dynamic and unbalanced. This leads us to a fascinating idea known as asymmetric dark matter. What if dark matter particles and their antiparticles are not identical? If they are different, their annihilations might not be perfectly efficient. Some particles could avoid destruction, building up with a specific charge or property. In the frenzied core of Messier 82, this asymmetry could create a bizarre cycle. The dark star at the center would continuously draw in fresh dark matter from its surroundings, but instead of annihilating all of it smoothly, the asymmetric interactions might cause the object to periodically expel a fraction of the incoming particles. It would function like a fountain, drawing dark matter in from the galaxy and spraying a portion of it back out in a high-energy jet or wind. This cosmic fountain would have a real, tangible effect on the visible galaxy. The expelled dark matter would carry energy and momentum, potentially stirring the already turbulent gas clouds. This stirring could compress some gas clouds, triggering the birth of new stars while dispersing others. In essence, the hidden dark star could be a puppeteer, its invisible outflows influencing the very starburst frenzy that defines the galaxy. Detecting such an object would require looking for a ghostly signal within a fireworks display. Astronomers would search for faint, persistent sources of high-energy radiation, like gamma rays or X-rays, emanating from the exact dynamical center of the starburst, a place already flooded with light from newborn stars and supernova. The fountain's signature would be a steady, pinpoint glow of specific particles amidst the chaotic variability. Finding it would revolutionize our understanding of dark matter's role in galactic evolution. It would mean that in the most active and violent stellar nurseries in the universe, an unseen heart may beat, not with fusion, but with the rhythmic inflow and outflow of shadow, sculpting the brilliant chaos we see from afar. A star's death is usually a spectacular affair, a brilliant supernova visible across galaxies. But what if a star could die in silence? Our eighth dark star candidate is not an object we can find, but one we might only hear in the aftermath of its violent end, the remnant of a dark supernova. To understand this concept, we must first revisit what a dark star truly is. It is a massive sphere, potentially hundreds of times the mass of our Sun, held in balance by the heat from dark matter annihilations at its core. This energy source is stable, but it is not eternal. Over billions of years, the dark star would gradually use up the annihilating particles in its heart. As this fuel depletes, the outward pressure weakens. Gravity, relentless and patient, would finally gain the upper hand. The star would begin an irreversible collapse. In a normal, fusion-powered star of similar mass, this collapse would rebound in a titanic explosion, blasting its outer layers into space in a flash that outshines entire galaxies. But a dark supernova would be a different beast entirely. Its outer layers are not the product of complex nuclear fusion. They are primarily simple hydrogen and helium. More critically, the core is not made of neutrons or other dense, familiar matter. It is a collapsing knot of dark matter. The resulting cataclysm would be almost invisible. There would be no brilliant flash of optical light, no expanding shell of glowing gas to mark its passing. The energy of the collapse would have to go somewhere, and it would emerge in the most ghostly of forms. The violent, asymmetric crumpling of such a massive object would send powerful ripples through the very fabric of spacetime itself, gravitational waves. Simultaneously, the extreme conditions could generate a tremendous burst of nearly massless particles called neutrinos, which stream through matter almost untouched. This means the death of a dark star would be a whisper in the dark, a tremor in the cosmic web, and a silent flood of phantom particles. This is where our most sensitive listening posts come in. Observatories like LIGO and Virgo are designed to catch the faintest ripples from colliding black holes and neutron stars. Their data is a library of cosmic crashes. Within that library, there may be signals that do not fit any known template. A gravitational wave signal from the very early universe, one with a strange frequency or pattern that cannot be explained by the merger of two black holes or neutron stars, could be the echo of a dark supernova. Future space-based detectors like the planned Laser Interferometer Space Antenna will listen for lower frequency waves, potentially from more massive and ancient events. An unexplained burst from the cosmic dawn, with no accompanying flash of light across the electromagnetic spectrum, would be a prime candidate. Discovering such a signal would be a profound revelation. It would tell us that dark stars not only lived but that they also died, and that their deaths left a unique signature written not in light, but in the bending of space and the flight of ghostly particles. It transforms a supernova from a spectacle into a secret, a final, violent confession from an object that spent its entire life hidden in shadow. While the death of a dark star might echo across spacetime, its life can define the very shape of a galaxy. Circling our Milky Way are faint, wispy satellites known as dwarf spheroidal galaxies, ghostly collections of ancient stars with almost no gas or new star formation. They are places like the Draco dwarf or the Sculptor dwarf, cosmic relics that seem to be held together by a secret. Their visible stars are spread thinly across a vast volume, yet they move at surprisingly high speeds. This tells astronomers one thing with certainty: these galaxies are absolutely dominated by dark matter. Their visible stars are just a few scattered lights floating in an immense, invisible ocean of mass. But the mystery deepens when we look at the distribution of that dark matter. Detailed studies of stellar motions suggest the dark matter isn't just a diffuse cloud. It is concentrated into an extraordinarily dense, compact halo right at the galaxy's very center. It is as if all that invisible weight is piled onto a single, central point. This leads us to our ninth candidate, the halo anchor. What if this compact core is not just a statistical peak in a dark matter cloud, but an actual physical object, a single, monstrous dark star serving as the gravitational heart of the entire dwarf galaxy? The concept is compelling. In the early universe, one of the first structures to form in a region destined to become a dwarf galaxy could have been a primordial dark star. Its immense gravity would then act as a seed, pulling in vast reservoirs of dark matter and the scant ordinary matter around it. Over billions of years, the visible stars would form and evolve, but their orbits would all be fundamentally shaped by the persistent, overpowering tug of this central, unseen titan. The halo anchor would be a stable, ancient engine, continuously annihilating dark matter particles at its core and glowing faintly with the resulting energy. Finding it, however, means looking for a needle in a cosmic haystack made of shadow. Astronomers are focusing their search on the precise dynamical centers of these dwarf galaxies. They are not looking for a twinkle of starlight, but for a faint, persistent pinpoint of high-energy radiation. As dark matter particles annihilate within the anchor, they should produce a predictable byproduct, a steady trickle of gamma rays and X-rays. The challenge is that this signal would be incredibly faint, easily drowned out by background cosmic noise. The strategy is one of meticulous exclusion. By pointing instruments like the Fermi Gamma Ray Space Telescope at the heart of a dwarf like Draco for years, scientists accumulate data. They are searching for any excess of gamma rays at a specific energy that cannot be explained by known pulsars, distant quasars, or other mundane astrophysical processes. A definitive detection would appear as a subtle but statistically significant bump in the data, a whisper of photons pointing directly to the galaxy's core. Discovering the halo anchor would solve a long-standing cosmic puzzle. It would provide a physical explanation for why these dark matter halos are so dense and compact, replacing an abstract distribution with a singular, massive object. It would mean that some of the smallest and faintest galaxies in our cosmic neighborhood are not just dominated by dark matter, but are literally built around a dark star, an ancient anchor whose silent gravity has dictated every stellar orbit since the dawn of time. The silent anchors of dwarf galaxies give way to one of the most visually stunning phenomena in the cosmos. A planetary nebula is often called a star's final masterpiece, a glowing shroud of gas expelled by a dying sun, illuminated by the hot ember of a white dwarf at its core. These structures, like the famous Cat's Eye Nebula, display astonishing complexity with intricate rings, jets, and symmetrical lobes that defy simple explanation. For decades, astronomers have modeled how the dying star's winds and radiation should sculpt this expanding cloud, yet some of the most beautiful formations remain puzzles. The delicate symmetry and powerful outflows seen in objects like the Cat's Eye suggest forces at work beyond a lone, fading white dwarf. This leads us to our 10th dark star, the imposter in a planetary nebula. The scenario begins with a binary system, two stars born together. One, a sun-like star, reaches the end of its life. It swells into a red giant and then sheds its outer layers, leaving its hot, dense core exposed as a white dwarf. This white dwarf then floods the expanding cloud with ultraviolet radiation, making it glow. But what if its companion was not another ordinary star? Imagine that second star was instead a dark star, a massive sphere of dark matter that had been orbiting silently for eons. As the visible star goes through its death throes, ejecting its atmosphere in a series of pulses and bursts, the gravity of the dark star companion would exert a profound and continuous influence. It would act like an invisible potter's hand, shaping the outflowing gas. The intricate patterns we see, the precise bipolar lobes, the concentric rings, even the violent jets that shoot from the poles, could all be signatures of this hidden partner's gravitational tug. The dark star would not contribute light, but it would contribute structure, its steady pull organizing chaos into breathtaking art. Detecting such an imposter requires looking past the brilliant glow to the motion beneath. Astronomers would use powerful spectrographs to map the kinematics of the nebula gas in extreme detail. They would measure not just how fast the gas is expanding, but the precise directions and velocities at every point within the nebula. A model based solely on the white dwarf's influence would predict a certain flow pattern. If the observed gas motions reveal strange gravitational eddies, areas where the gas is being pulled or twisted in ways the visible core cannot account for, it points to an unseen mass. It would be like studying the ripples on the surface of a pond. If you see perfect concentric circles, you know a single stone was dropped. But if you see complex interference patterns, crossing ripples and unexpected swirls, you know a second, hidden stone must have fallen nearby. By creating a detailed gravitational map from the gas motions, scientists could pinpoint the location and approximate mass of the dark companion. Finding the imposter would transform our understanding of these cosmic tombstones. It would mean that some of the sky's most beautiful objects are not solo acts, but duets between a fading ember of light and a permanent sphere of shadow, their combined history written in the luminous geometry of sculpted gas. Gravity writes its signature not just in the motion of stars, but in the birth of them. Our search now takes us to a neighboring galaxy, the Large Magellanic Cloud, a satellite of the Milky Way ablaze with the pink glow of stellar nurseries. Here, astronomers hypothesize a unique system could be at work, a pair of dark stars locked in a mutual orbit, a dark twin system. Unlike the solitary rogue wanderer, these two objects would form a binary, circling each other in a tight, silent dance over millions of years. Their combined mass would be staggering, and it is this shared gravitational influence that could make them detectable. Imagine two massive, invisible spheres whirling around a common point, their motion creating a subtle but persistent ripple in the fabric of their surroundings. This twin system would be embedded within a vast, shared halo of dark matter, a dense, invisible cloud that extends far beyond the individual stars themselves. As this binary pair moves through the Magellanic Cloud, its immense combined gravity would act like a cosmic plow, sweeping through the galaxy's diffuse gas and dust. The effect would be most pronounced in regions already on the verge of collapse. The gravitational wake of the passing twins could compress interstellar clouds, triggering the formation of new, young star clusters in its path. Conversely, in other areas, the tidal forces might tear fragile clouds apart, stifling star formation. The result would be a strange pattern on the galactic map, a trail of stellar birth and disruption that seems to have no visible cause. To find the dark twin system, astronomers would not look for a single point of light, but for a correlated pattern of motion. They would meticulously chart the positions and velocities of young star clusters and gas clouds across the large Magellanic Cloud. The key would be finding a series of these objects that are not only disturbed, but are all moving in a way that suggests they are being gravitationally shepherded by a single, massive, and invisible source. It would be like studying the surface of a pond after a boat has passed. You do not see the boat itself, but you can trace its path by the specific pattern of waves and ripples left behind on the water. The clusters influenced by the dark twins would show a coherent drift, a subtle streaming motion that points back to the binaries' predicted location. Confirming such a signal requires ruling out every other possibility, from the gravitational pull of known stellar clusters to the large-scale dynamics of the galaxy itself. It is a forensic analysis of gravity's fingerprint on a galactic scale. Discovering this binary pair would be a monumental find. It would prove that dark stars can form in pairs, just like ordinary stars, and that their collective gravity can actively shape the evolution of galaxies. These silent twins dancing in the heart of a neighbor galaxy would be architects of light, their unseen mass writing its story in the birth and motion of the very stars we can see. The idea of a star born before time itself seems to defy every law of physics we know. Yet, on the farthest edge of theoretical cosmology, a possibility exists for a dark star that is not merely ancient, but truly primordial in a way that rewrites the word. This is our 13th candidate, the relic from before the Big Bang, a concept that pushes the boundaries of science into the realm of the profound and nearly unimaginable. To even approach this idea, we must step beyond the standard model of a single, definitive beginning. We must consider theories like conformal cyclic cosmology, proposed by physicists like Roger Penrose. This model suggests our universe is not the first and only one, but simply one cycle in an endless series. In this view, a previous eon, a prior universe, expanded and faded into a state of maximum entropy, a vast, cold, featureless expanse. But within that emptiness, remnants could have persisted, ultra-dense, timeless objects stripped of all scale and matter as we know it. As the new Big Bang ignited our current cycle, these relics would be imprinted into the fabric of the newborn cosmos as seeds of extreme density. One such seed could be the core of our dark star relic, a knot of something that is not quite matter and not quite energy as we define them, a fossil from a reality that came before our own. An alternative framework is the theory of eternal inflation, which paints a picture of a multiverse bubbling with endlessly spawning universes. In this chaotic froth, it is conceivable that a chunk of ultra-dense material from a neighboring universe could have tunneled or been ejected into our own during its violent birth. This foreign fragment, composed of particles and forces alien to our cosmos, would then clothe itself in our universe's dark matter and gas, becoming a dark star powered by annihilation processes we cannot fully comprehend. The relic would be an anomaly in every sense. Its internal composition, the very rules governing its core, might be subtly different from anything that formed naturally within our cosmic timeline. Its gravitational signature or its emission of particles might carry an odd, inexplicable fingerprint, a set of properties that simply do not fit our models of stellar evolution or dark matter behavior. Finding such an object would be the ultimate cosmic detective story, requiring us to identify an outlier among outliers. Astronomers would need to find a dark star candidate that, upon deepest inspection, breaks one too many rules. Perhaps its calculated mass is implausibly high, or the spectrum of radiation from its annihilation shows impossible energy spikes. Maybe its location is statistically absurd, sitting exactly at a point of cosmological significance that defies random chance. Proving its extraneous origin, however, would be a challenge bordering on philosophy. The discovery would be less about pinpointing a location and more about demonstrating an irreconcilable contradiction to our entire history of the universe. It would force us to confront the possibility that our cosmos is not a solitary event, but a chapter in a much grander, perhaps infinite, story. While this idea resides firmly in the realm of fringe science, its value is incalculable. It stretches the imagination to its limits, reminding us that the darkest corners of space might hold not just hidden objects, but hidden histories. The search for a relic is the search for a message in a bottle from a shore we did not know existed, a single piece of evidence that our reality is not the first and may not be the last. The profound mystery of what dark matter actually is brings us to a candidate built from a specific, ghostly particle. Our 14th dark star is the axion star candidate, a theoretical object that ties the largest cosmic structures to the tiniest quantum realms. Axions are hypothetical particles, incredibly light and born from a solution to a fundamental problem in particle physics. If they exist, they are a perfect fit for cold dark matter, streaming through the universe in vast numbers. But under the right conditions, these particles could do something extraordinary. They could condense. Picture a cloud of gas cooling until its atoms fall into the same quantum state, forming a superfluid known as a Bose-Einstein condensate. In principle, a vast cloud of axions could undergo a similar process on a cosmic scale, collapsing under their own gravity into a single, coherent quantum object millions of kilometers across, yet with the mass of a star. This is an axion star, a giant, fuzzy sphere where trillions upon trillions of particles behave as one single wave. Unlike the annihilation-powered dark stars we have discussed, an axion star's primary interaction with the visible world would be through a delicate quantum conversion. Axions are theorized to interact very weakly with magnetic fields. In the presence of a strong magnetic field, such as those surrounding neutron stars or within galactic cores, the axions in the star could spontaneously transform into photons, particles of light. This would produce a faint, highly specific radio signal. The key signature is its oscillation. Because the axion has a specific, albeit tiny, mass, the photons produced would have a correspondingly precise frequency, like a single pure note being played on a cosmic radio. The entire axion star would hum with this frequency, a steady, monochromatic whisper amidst the chaotic radio noise of the universe. Hunting for this whisper is the goal of experiments like the Axion Dark Matter Experiment, or ADMX. This is not a telescope pointed at the sky, but a sophisticated instrument housed in a laboratory, designed to listen for axions converting within a powerful magnetic field. It functions as an ultra-sensitive radio receiver, tuned to scan through millions of possible frequencies, seeking that one telltale spike that would betray the axion's presence. While ADMX primarily searches for a diffuse background sea of axions, the detection of a strong, localized signal could, in theory, point to a concentrated source, an axion star. The challenge is that the predicted frequency of this signal is unknown, requiring a painstaking, years-long scan across a vast range. Finding it would be a dual discovery of monumental proportions, identifying both the particle that makes up dark matter and a completely new class of stellar object. It suggests that some dark stars may not be engines of destruction, but ethereal quantum spheres singing a faint, steady song into the magnetic winds of the galaxy, waiting for the right instrument to finally tune in. Far from the crowded galactic core, our galaxy's true frontier begins. The Milky Way's halo is a vast spherical cloud of ancient stars, globular clusters, and dark matter, extending hundreds of thousands of light years into the emptiness. Here, where the pull of our galaxy is weak and the stars are few and far between, another kind of wanderer could drift in silence. This is the galactic halo wanderer, a dark star that remains bound to the Milky Way, yet travels a lonely, looping orbit far beyond the bright spiral disk we call home. Its existence speaks to the chaotic assembly of our galaxy, a relic perhaps captured from a devoured dwarf galaxy long ago and flung to the outermost reaches. Detecting such an isolated object presents one of the most formidable challenges in astronomy because it offers almost nothing for us to see. There is no background of nearby stars for it to gravitationally perturb, and its own faint glow from dark matter annihilation would be hopelessly lost in the darkness. The only chance to catch the halo wanderer is a fleeting moment of perfect cosmic alignment, an event so rare it borders on statistical magic. This method is called extreme microlensing. Imagine the dark star on its multi-million-year journey through the halo passes almost perfectly between our telescopes and a single, distant star in another galaxy, perhaps the Andromeda Galaxy. For a brief period, its gravity acts as a natural lens. It bends and focuses the light from that faraway star, causing it to temporarily brighten in a very specific way. The star would appear to grow brighter over days or weeks, peak, and then fade back to its normal luminosity, tracing a smooth, predictable curve of light. This event would be a one-time gift, a flash in the data that cannot be repeated or studied at leisure. The statistical challenge is immense. Our telescopes monitor millions of stars in galaxies like Andromeda precisely to catch these microlensing events, which are already rare. Most are caused by ordinary, faint stars or stellar remnants like white dwarfs or neutron stars within the halo. To claim a detection as a dark star, astronomers must do more than just record the event. They must analyze the light curve with exquisite precision. The duration and shape of the brightening reveal the mass of the lensing object. A dark star with a mass hundreds of times that of our Sun would create a lensing event that lasts significantly longer than one caused by a typical star. Furthermore, deep follow-up observations at the exact location of the event would show absolutely nothing. No dim red dwarf, no cooling white dwarf, no trace of a visible object at the lens's predicted distance. It would be a mass without light, a gravitational signature without a source, confirming a single event as a dark star, rather than a more common dim stellar remnant, requires ruling out every other possibility with near certainty. It is a forensic argument built on absence, duration, and the complete failure to find any conventional explanation. A convincing case would likely require not one, but several such anomalous events, all pointing to the same conclusion: massive, dark objects drifting in the galactic halo. Finding the halo wanderer would be a triumph of patience and statistical rigor, proving that even in the emptiest realms of our own galaxy, shadows from the dawn of time continue their slow, silent orbits, their presence revealed only in the brief, magnified twinkle of a star in another galaxy entirely. The vast emptiness of a galactic halo is one thing, but what about the space between galaxies themselves? The Virgo cluster is a sprawling metropolis of over 1,000 galaxies, all bound together by gravity in a region of space millions of light years across. Within this immense city of stars, a different kind of small community might exist. Our 16th, 17th, and 18th candidates are the triplet in the Virgo cluster, a small, dark family of 3 dark stars, bound not to any single galaxy, but to each other, drifting through the intergalactic void. Think of them as a shadowy analog to a tiny, dark star cluster, a miniature system where the only thing holding them together is their mutual gravitational attraction, a trinity of invisible giants. Their location is key. they would float in what astronomers call the intracluster medium, the thin, superheated gas that fills the spaces between the cluster's galaxies. This gas is not perfectly smooth. It has ripples and flows stirred by the gravitational tides of all the passing galaxies. The combined mass of the three dark stars, perhaps totaling 1,000 times the mass of our Sun, would be significant enough to make a tiny dent in this environment. As they move, their shared gravity would gently tug at the surrounding hot gas, creating a subtle wake, a barely perceptible density wave rippling through the intracluster medium. Detecting this wake is a monumental task. It would require mapping the hot gas in the Virgo cluster with incredible precision, using X-ray telescopes to chart its temperature and density in fine detail. Scientists would search for small, coherent disturbances in the gas that have no visible galaxy or star cluster to explain them. It would be like trying to spot the wake of a submarine from an airplane by looking for a faint pattern on the surface of a choppy, stormy ocean. The signal would be incredibly weak, buried in the chaotic motions driven by the cluster's enormous scale. Another method relies on the triplet's gravity bending the light from even more distant galaxies far behind the Virgo cluster. This is weak gravitational lensing on a very small scale. Instead of creating dramatic arcs, the three dark stars would impose a minuscule, coordinated distortion on the shapes of hundreds of background galaxies. Their combined mass would warp the local spacetime just enough to very slightly align the orientations of those distant, faint smudges of light. Finding this signal is a statistical nightmare. Astronomers must analyze the shapes of tens of thousands of galaxies, meticulously subtracting the much larger lensing effects caused by the cluster's overall mass and its individual giant galaxies. They would be searching for a tiny, residual pattern, a whisper of extra distortion that seems to follow a specific, moving point in the intergalactic darkness. The triplet represents a new level of complexity in the hunt. It is not one dark star, but a system of them, and not in isolation, but in the most crowded extragalactic neighborhood we can easily study. Finding them would mean dark matter can form not just singular objects, but small, bound societies that exist entirely outside the boundaries of galaxies. Their silent dance felt only in the gentle stirring of million-degree gas and the faint shearing of ancient light. The line between a shadow and an abyss can be incredibly thin. Our 19th candidate exists in that very blurry space, an object we are calling the primordial black hole mimic. Picture a dark star that has grown so massive and collapsed so far under its own gravity that it becomes incredibly dense and compact. To any telescope observing it from afar, its signature would be nearly indistinguishable from that of a black hole. It would warp spacetime with immense gravity. It would bend the light from stars behind it, and if it were accreting gas from a companion, it would likely produce the same brilliant X-ray flares we associate with black hole feeding frenzies. For all observational purposes, it would look like a black hole, yet a fundamental theoretical difference would remain. A black hole, in its simplest form, is defined by its event horizon, a point of no return where gravity becomes so strong that not even light can escape. Inside that boundary lies a singularity, a point of infinite density where our laws of physics break down. The primordial black hole mimic, however, would have a physical surface. It would not be a point of infinite collapse, but a stable, ultra-dense sphere of dark matter, still powered by annihilation at its core. This surface, while unimaginably dense, would be a real boundary. Matter could, in principle, strike it. Light could, theoretically, reflect from it, even if that reflection is instantly swallowed by the incredible gravity. This subtle distinction is everything. It means the object is not a true hole in space-time, but the most extreme star imaginable. The challenge, then, is how to tell them apart when they look so similar from a distance. The answer lies in the future of extreme astronomy. Projects like the Event Horizon Telescope, which captured the first image of a black hole's shadow, are just the beginning. The next generation of instruments, perhaps space-based arrays with even higher resolution, aim to do more than just confirm a shadow. They will attempt to scrutinize the very edge of these dark objects. Scientists will look for a specific telltale sign, the absence of an infinitely dark circle. If an object has a surface, even one that is nearly perfectly dark, there is a chance that a minuscule amount of light or thermal radiation could emanate from it, or that material crashing onto it would create a different kind of flash than material disappearing past an event horizon. The key signature would be found in the precise shape and darkness of the shadow's edge. A perfect event horizon creates a specific, clean shadow predicted by general relativity. A physical surface, however, might produce a slightly fuzzier or differently shaped dark region due to effects of plasma or emissions right at the boundary. Detecting this difference would require observations of incredible precision, likely targeting the supermassive object at our galaxy's core, Sagittarius, a star, or a similar giant in a nearby galaxy. Finding a mimic would be a discovery that forces us to rewrite our cosmic classifications. It would mean that some of the objects we have confidently labeled as black holes might in fact be something else entirely, dark stars that reached the very brink of becoming a whole but stopped, held in final, fierce balance by the ghostly physics of dark matter annihilation. It suggests that the darkest things in the universe might still have a skin, a final surface where the shadow ends and the star, however strange, begins. A pulsar's rhythm is the heartbeat of a dead star, but what if the cosmos has a pulse we cannot hear with radio ears? Our 20th dark star candidate is the dark pulsar, a rapidly spinning sphere of dark matter that broadcasts its existence not in light but in the periodic tremor of spacetime itself. This object takes the concept of a dark star and adds a dynamic, rotating twist. Just as ordinary pulsars are born from the collapse and rapid spin of a massive star's core, a dark pulsar could form through a similar violent genesis. Perhaps it is the remnant of a dark supernova, the collapsing core of a failed dark star that somehow retained a tremendous angular momentum. As it shrank, it would have spun faster and faster, conserving its rotation like a cosmic figure skater pulling in their arms. The result would be a dense, dark sphere completing a full rotation in mere milliseconds. But unlike a normal pulsar, which has powerful magnetic fields that funnel radiation into lighthouse-like beams, the dark pulsar's energy output would be fundamentally different. Its power would come from the continuous accretion and annihilation of dark matter, a process that could be uneven across its surface or within its structure. This asymmetry, combined with its blistering spin, would make it a potent periodic source of gravitational waves. Each tiny bump or density fluctuation on its surface, whirling around at a significant fraction of the speed of light, would create a rippling distortion in spacetime that propagates outward like the steady beat of a drum. The frequency of these gravitational waves would be directly tied to the spin rate of the dark pulsar, creating a potentially detectable, repeating signal in the otherwise stochastic background of cosmic ripples. This leads to a fascinating possibility for indirect discovery. Our most precise tools for measuring time are not atomic clocks on Earth, but millisecond pulsars in distant space. These neutron stars spin with unbelievable consistency, their radio pulses arriving with a predictability that rivals the best human-made timepieces. Astronomers use networks of these pulsars as a galaxy-spanning detector, a pulsar timing array. They monitor the arrival times of pulses from dozens of these cosmic clocks. The passing of a gravitational wave from a distant event, like colliding black holes, will minutely stretch and compress the space between us and the pulsar, causing its pulses to arrive very slightly early or late in a correlated pattern across the array. Now consider a dark pulsar in our galactic neighborhood. Its steady, periodic gravitational wave signal would act as a continuous, low-frequency hum in the fabric of the galaxy. As these waves pass through the pulsar timing array, they would imprint a specific rhythmic pattern onto the arrival times of all the monitored pulsars. It would not be a single event, but an ongoing, persistent signal. Scientists would search the timing residual data, the tiny discrepancies between predicted and actual pulse arrival times, for a common oscillation. Finding a single frequency that affects all the pulsars in the array in a predictable way would point to a continuous spinning source of gravitational waves. The next step would be to triangulate its location in the sky by analyzing the subtle differences in how the signal affects each pulsar based on its position relative to the source. This would be the ghostly fingerprint of the dark pulsar, its spin rate and rough location revealed not by any flash of light, but by the systematic way it makes the universe's most perfect clocks ever so slightly stumble in unison. Discovering such an object would open a new window into the dark sector, revealing that dark matter structures can not only exist but can spin, vibrate, and ring like a bell, sending out tremors that gently nudge the ticking of distant stellar hearts. The stellar traffic jam around our galaxy's core hides a ghost among the crowd. In the inner light year surrounding Sagittarius, a star, a dense cluster of stars whips around at unbelievable speeds, their orbits tracing a frenetic ballet dictated by the black hole's immense gravity. Among these visible dancers, a single participant might be completely invisible, a galactic center cluster member. This dark star would not be a lone parasite, but one member of a vast stellar family, its mass contributing to the collective gravitational field that shapes the motions of all its luminous siblings. The method to find it relies on the precise choreography of chaos. Astronomers use sophisticated computer programs called N-body simulations to model this star cluster. They input the known masses, positions, and velocities of every visible star they can map, along with the dominant gravity of the central black hole, and then let the simulation run forward in time. The virtual cluster evolves, stars interacting, their orbits shifting through mutual gravitational tugs. The goal is to produce a simulation that perfectly matches what we actually observe today. But there is a recurring snag. When scientists compare their best simulations to the real, observed motions of stars like the famous S-cluster, they often find discrepancies. The visible stars sometimes move in ways the simulated gravity of their neighbors and the black hole cannot fully explain. It is as if an unseen hand is gently nudging them, a persistent perturbation that suggests extra mass is hidden within the cluster itself. This is a missing mass problem on the smallest, most precise scale imaginable. The hypothetical dark star would be the solution. Its substantial mass, perhaps tens or hundreds of times that of our Sun, would exert a continuous, localized pull on the stars nearest to it in the cluster. Over time, its influence would warp their orbits in a specific, subtle pattern. The key to pinning it down is statistical. By running thousands of simulations, each with a different configuration of hidden mass, astronomers could search for the one model where inserting a single, massive, dark object at a specific coordinate finally makes the virtual star cluster match the reality we see through our telescopes. The cluster member's signature would be a collective wobble, a shared anomaly in the paths of several nearby visible stars that all point toward the same empty point in space. Finding it would require not just a snapshot, but a decades-long movie of stellar motions in the galaxy's most extreme environment. Each new observation of a star's position refines the map, tightening the constraints on where any hidden mass must be. This dark star candidate turns the entire stellar cluster into a detection instrument, using the delicate gravitational interplay between stars to outline the shape of an absence. It suggests that even in the most brilliantly lit and carefully studied place in our galaxy, a shadow may be moving with the crowd, its presence written only in the slight, collective stumble of its visible neighbors. The smooth, ghostly arcs of star streams are the scars of our galaxy's violent past. When a small dwarf galaxy ventures too close to the Milky Way, our galaxy's immense gravity does not just capture it, it shreds it. Over billions of years, the dwarf is torn apart, its stars strewn across the sky in long, elegant ribbons that trace its final, doomed orbit. These stellar streams, like the one known as GD1, are perfect cosmic fossils, their undisturbed shapes telling the story of that ancient encounter. Yet, some of these streams are not perfectly smooth. GD1, for instance, has a curious gap, a place where the line of stars seems to be severed or perturbed. One compelling explanation for this disruption could be our 22nd candidate, the rejuvenator in a star stream. Imagine a dark star, perhaps one that was once the central anchor of that devoured dwarf galaxy, or a rogue object from elsewhere in the halo. As it journeys through the Milky Way, its path intersects the delicate stellar stream. Even a single, close flyby would be a gravitational catastrophe for such a fragile structure. The dark star's substantial mass would act like a stone thrown into a still pond, but instead of water, it sends ripples through the line of stars. As it passes, its gravity would give a sharp, sudden tug to every star in its vicinity. Stars directly in its path could be kicked out of the stream entirely, creating a gap. Stars on either side could be accelerated or slowed, bunching up in some areas and stretching out in others, creating a visible kink or wiggle in the otherwise smooth arc. The rejuvenator would not destroy the stream, but it would permanently scar it, leaving a fingerprint of its passage written in the altered motions of thousands of suns. Detecting this requires turning the stream itself into a detector. Astronomers use powerful telescopes to map the precise positions, distances, and velocities of individual stars within a stream like GD1. They then run sophisticated simulations, modeling how the stream should look based solely on the Milky Way's gravity. When the real data shows a gap or a bend that the model cannot reproduce, the search for a cause begins. By simulating the flyby of a massive, compact object through the stream, scientists can test whether such an event could recreate the exact distortion they see. They would vary the mass of the intruder, its speed, and its trajectory, looking for a match. If a simulation with a dark, star-sized mass perfectly repairs the stream's shape in the model, it points strongly to an unseen culprit. Finding the rejuvenator would be a masterstroke of galactic archaeology. It would mean that by studying the wounds in these stellar fossils, we can not only learn about the galaxies that were destroyed, but also map the passage of invisible giants that have wandered through the galactic graveyard. The dark star becomes a ghostly sculptor, its brief, ancient encounter leaving a permanent scar that we can decode billions of years later, a silent witness to the dynamic, ever-changing nature of our galactic home. The universe's most powerful explosions leave a lingering whisper in the form of high-energy gamma rays. Orbiting high above Earth, the Fermi Gamma Ray Space Telescope has spent over a decade mapping this violent sky, cataloging thousands of brilliant sources from pulsars to distant quasars. Yet a persistent few remain stubbornly anonymous, points of intense gamma radiation with no visible star, galaxy, or nebula to explain them. These are the unassociated Fermi sources, and one of them could be our 23rd dark star candidate, a silent sphere broadcasting its existence through the annihilation of its very substance. The process is direct. If a dark star is composed of certain types of dark matter particles, then those particles, when they collide with their antiparticles, would annihilate completely. This annihilation converts their mass directly into energy, often producing a cascade of secondary particles that ultimately decay into gamma rays, the highest energy form of light. A stable dark star would therefore glow faintly but persistently in gamma rays, a steady beacon unlike the erratic flashes of a pulsar or the chaotic blaze of a supernova remnant. The signature would be a combination of location and spectrum. First, the source must be truly dark at all other wavelengths. Deep follow-up observations with optical, infrared, and radio telescopes would reveal absolutely nothing at the precise coordinates of the gamma ray signal, ruling out every known class of visible object. Second, and more crucially, the energy spectrum of the gamma rays must match the predicted fingerprint of specific dark matter particle annihilations. This is not a smooth curve, but would show subtle bumps or cutoffs at very specific energies, a direct translation of the dark matter particle's mass into light. One particularly intriguing example is Fermi Source 3 FGLJ221 2.5 plus 0 705.4, a bright and steady gamma ray emitter located in a seemingly empty patch of sky. Despite extensive searches, no pulsar, no distant galaxy, no remnant has been found to account for its output. Its gamma-ray profile is consistent with some theoretical models of heavy dark matter particle annihilations. It sits a question mark etched in pure energy. Another candidate is 3 FGLJ 1745.3-3018, located towards the galactic center but offset from the crowded plane. Its steady emission and lack of a multi-wavelength counterpart make it a prime subject for this dark star hypothesis. Discovering that one of these anonymous sources is a dark star would be a transformative moment. It would mean that for over a decade, we have been receiving the death cries of invisible particles from a giant, hidden star, a message written in the universe's most penetrating light, waiting for us to finally understand its origin. Gamma rays are the final, brilliant scream of annihilating particles, but the true story of dark stars might be told in a far quieter language. Beneath the detectable chirps of black hole mergers, the universe holds a persistent, low-frequency hum, a murmur woven from countless ancient collisions. This is the stochastic gravitational wave background, and our 24th dark star is not a single object but a population, a lost civilization of giants whose final acts still echo through spacetime. They are the gravitational wave background contributors. In the universe's first billion years, when it was smaller, denser, and swarming with dark matter, these colossal objects would have been far more common. Drawn together by their immense gravity, pairs of dark stars would have spiraled inward over eons, eventually merging in catastrophic unions. Each collision would have been a silent, invisible cataclysm, unleashing a powerful burst of gravitational waves, ripples in the fabric of reality itself. But unlike the sharp, distinct chirp from a nearby black hole merger, these signals are impossibly distant and overlapping. They come from every direction and every moment in the cosmic dawn, blending together into a steady, undulating sea of spacetime distortion, a fossilized record of violence from the age when dark stars may have ruled. We are now on the cusp of hearing this cosmic murmur. The tool for this discovery is not a telescope that sees light, but a galaxy-sized detector made of time itself, pulsar timing arrays. By monitoring the ultra-precise rhythms of dozens of millisecond pulsars scattered across the Milky Way, astronomers are listening for a common disturbance. As gravitational waves from this background wash through our galaxy, they minutely stretch and compress the space between us and each pulsar. This causes the pulsar's clockwork ticks to arrive very slightly early or late in a correlated, symphony-like pattern across the entire array. The expected signal is a low, rumbling hum, often attributed to the combined din of merging supermassive black holes throughout cosmic history. But what if the hum we finally detect is not quite what we predicted? The key to implicating dark stars lies in the frequency and amplitude of this background. The mergers of dark stars, given their potentially enormous masses and the era in which they would have been most active, could imprint a unique signature onto this gravitational wave sea. It might be louder at certain frequencies than models of black hole mergers can account for, or it might have a spectral shape that points to a different population of colliding objects entirely. An anomalous signal, one that cannot be fully explained by black holes alone, would be a tantalizing clue. It would suggest that another type of massive, compact object was abundant in the early universe, colliding frequently and contributing its own chorus to the spacetime hum. Finding this population would be an indirect but profound discovery. we would not pinpoint a single dark star, but we would uncover the statistical ghost of an entire lost generation. Their collective deaths, a symphony of silent crashes from the dawn of time, would have left a permanent warp in the background of reality, a hum that has been traveling for over 12 billion years to reach our most sensitive instruments. It transforms the search from hunting for a single shadow to listening for the echo of an ancient war, a battle of titans fought in absolute darkness whose final tremors are only now arriving. This final candidate is not a place but a possibility. The ultimate dark matter laboratory is a dark star in its most ideal, concentrated form, a perfect sphere of almost pure dark matter so dense and stable it becomes a natural experiment in particle physics. Its very existence would answer the most fundamental questions we have about the invisible substance that shapes our cosmos. The first critical test would be determining what kind of particle it is made of. Is the dark matter inside it fermionic, composed of particles that, like electrons, cannot occupy the same quantum state? Such a fermionic dark star would have a maximum possible mass, a limit set by quantum degeneracy pressure, just as a white dwarf or neutron star does. Observing its mass would give us that limit, revealing the inherent mass of the individual dark matter particles themselves. Or is it bosonic, made of particles like photons or axions that can condense into a single quantum wave? A bosonic star would have no such hard mass limit and could, in theory, grow to truly monstrous sizes. Measuring the size and mass relationship of a real dark star would immediately tell us which family of particles dominates the dark universe. Beyond its composition, this laboratory would reveal how dark matter interacts with itself. Does it feel forces other than gravity? The stability of the dark star's structure holds the answer. If it is held together solely by gravity, it might be more diffuse. But if the dark particles inside have some additional, weak self-interaction, a short-range force that allows them to scatter off one another, that would provide extra pressure, changing the object's density profile and how it responds to disturbances. Watching how such a star reacts to a close encounter with a normal star or a cloud of gas could reveal this hidden force. Even its interaction with normal matter beyond gravity could be tested. If a stream of ordinary hydrogen gas were to fall onto its surface, would it simply pass through, barely noticing the dark matter, or would there be a faint, detectable interaction, a spark of radiation from collisions? The dark star becomes a target in a cosmic particle collider, with the universe itself providing the beam. Finding any one of these 25 dark stars would be far more than adding a new class of object to our catalogs. It would rip open a direct window into the nature of 85% of the universe's matter. For the first time, we would move from mapping dark matter's gravitational shadow to studying its substance. We would have a tangible specimen to probe, its mass, its size, its light, and its silence telling us the story of particles that have evaded our detectors for a century. The search for these undiscovered giants is a hunt for the ultimate keys to reality, hidden in plain sight across the vast darkness, waiting to transform our shadowy sketches of the cosmos into a complete and luminous picture. The search for these invisible giants demands a new kind of astronomy, one that listens as much as it looks. We cannot simply point a telescope and hope to see a dark star. We must build a net woven from every signal the universe provides. The hunt is a symphony of indirect methods, each instrument tuned to a different whisper of their existence. Our current tools are already sketching the outlines of this shadowy realm, but the next generation of observatories will bring the picture into startling focus. Consider the silent ripples in spacetime. Ground-based detectors like LIGO and Virgo have opened our ears to the violent chirps of black hole mergers. The future, however, lies in space. The Laser Interferometer Space Antenna, or LISA, is a mission designed to listen for the lower frequency hum of the cosmos. While LIGO hears the final, frantic seconds of a collision, LISA will detect the slow, centuries-long dance of massive objects spiraling toward each other. It could catch the gravitational wave signature of a dark star binary system millions of years before its final merger, or even detect the steady, rhythmic pulse of a spinning dark pulsar, a constant tone in the cosmic background. This is not just about hearing crashes, but about listening to the music of massive, hidden objects in motion. While LISA listens to the fabric of space, other missions are perfecting the art of cosmic cartography. The Gaia satellite is already revolutionizing our view of the Milky Way by mapping the precise positions and motions of over 1 billion stars with unparalleled accuracy. Its data is the ultimate tool for finding gravitational anomalies. By tracking the subtle, unexplained wobbles in stars like those in the Galactic center cluster or in the serene orbits of pulsars, Gaia and its successors can point directly to the location of unseen mass. It turns the entire galaxy into a vast gravitational sensor, where every star is a data point tracing the influence of the shadows between them. For the loneliest dark stars, the ones drifting in voids or halos, we turn to the statistical magic of microlensing. Current surveys watch millions of stars, hoping for that one in a million alignment. The future Nancy Grace Roman Space Telescope will transform this from a hopeful gamble into a systematic census. With a field of view 100 times larger than the Hubble Space Telescope, Roman will monitor hundreds of millions of stars in the Andromeda Galaxy continuously. It will catch thousands of microlensing events, building a vast statistical picture. Within that data, the outliers will shine, events caused by lenses that are too massive, too long in duration, and completely dark. Roman will not just find a single rogue wanderer, it will tell us how many of them are out there. The ultimate key, however, is combining all these senses at once. This is the power of multi-messenger astronomy. Imagine a scenario where a gravitational wave observatory like LISA detects the characteristic signal of two massive, compact objects merging in a distant dwarf galaxy. At nearly the same instant, a gamma-ray telescope like Fermi sees a faint, fading glow from the same patch of sky, the last photons from annihilating dark matter stirred up by the collision. Meanwhile, a neutrino observatory buried deep in Antarctic ice records a simultaneous burst of these ghostly particles. This coordinated signal, a chorus across gravity, light, and neutrinos, would be the undeniable fingerprint of a dark star merger. No known object could produce such a combined signature. It is this convergence of evidence that will move a dark star from a tantalizing hypothesis to an established fact of the cosmos. The hunt is a collaborative puzzle on a galactic scale, requiring patience, precision, and the willingness to listen to the universe in every language it speaks. From the silent heart of the Boötes void to the frenzied core of our own galaxy, this journey across 25 undiscovered dark stars has mapped a hidden cosmos. We have envisioned ancient giants anchoring dwarf galaxies, silent partners shaping planetary nebulae, and lonely wanderers drifting through intergalactic space. Each candidate, from the primordial behemoth to the gravitational wave contributor, represents a serious frontier in theoretical astrophysics, not mere science fiction. These are the guideposts for our most advanced telescopes and detectors, the specific, tantalizing targets that give shape to our questions about dark matter. The search itself transforms our relationship with the universe. It teaches us that discovery often begins not with a brilliant flash, but with a subtle anomaly, a wobble in a star's motion, a gap in a stellar stream, or a hum in the fabric of space-time. To seek a dark star is to embrace the profound mystery of the unseen, to let gravity and imagination chart a course through the darkness. As new observatories open their eyes and ears to the cosmos, remember that the greatest revelations are still waiting in the shadows. Stay curious, follow the data, and keep looking up, for the next chapter in this story will be written not in light, but in the silent, gravitational language of the universe itself.